This is a trajectory problem. Let's start with what we know about a projectile's vertical position. If you want to know where it's going to end up, you'll need to know where it started, plus its initial vertical velocity, usually vi sine theta or nothing, and you'll need to account for gravity. The one thing you absolutely must know is what time you want to get there. What if you don't know what time you want to get there? What if instead of a picture of the rocket in time, where the rocket is shot straight up and we want to know when it will land, we want a picture of the rocket in space, not y of t, but y of x. We need to somehow find a way to express t as a function of x, where we are. And once we've finished this equation, we need to substitute it back here and here until our final equation, not t, but x, tells us where we're going to be at every point of the graph. Not just y final when the problem is over, but over here and over here, in case there's something we very much want to hit or possibly want to miss. Just give us the horizontal location, delta x, of where it is relative to where we started, and this equation should give it to us. We're expecting something like this. And now we need to substitute and solve for the rest of the equation. One trig identity should make this process a lot easier for you. In your final equation, you can include terms for vi, the initial launch velocity, and theta, the angle from which the projectile was launched. Next equation that's handy to have around is an equation for maximum height. We can call this y max. It's all the way from the top of the path to ground level. Note that you're going to have already a term for yi or h. You want to find out how high that rocket will go given where it's been already. Again, you can have terms in your equation like vi and theta and g. What you don't want is t. As before, you might want to consider finding the time it's going to take to get to here, up at the top of the path, where you know one very important fact. What is it? Solve. Now, let's change sports. This is good for basketball and baseball. This is good for rocketry or anything else where you're trying to achieve a certain height, but you don't care where you get to that height. This is golf. Range is different than x max. It's not just how far you go horizontally. It's how far you go when you've returned to your original height. Notice that the range formula does not allow you to start at a certain yi or a certain height. You go all the way up, you come already down, right back to where you started. Of course, you will be solving for delta x, but it's delta x under a certain very specific set of conditions. And it's worth noting here that the question of airtime ought to be a very straightforward one. For instance, if you've done maximum height already, look at this parabola here. Look at the symmetry. Notice that it's symmetrical in time as well as in space. This side of the parabola is identical to this side of the parabola. So let's say it takes 3 seconds to get to the top of the arc. How long will it take in total to get to the bottom? Think about it. If you have your time to get to the maximum height, might you, with a little bit of massage, be able to figure out the time it takes to go all the way up and all the way down without doing much additional algebra? If true, would you then be able to solve for the range? Again, you can expect another trig identity in one of these two places to make your messy formula a good deal more compact. If you have derived all 3 of these formulas in your own handwriting, you may use them on projects, quizzes, and tests in every physics class hereafter. Be warned, this setup does not give you horizontal location in all cases. It is very, very specific to range. And range means right back where you started. Why? Because if you don't have the left side and the right side of that parabola be absolutely identical, then your calculation for time is going to look very, very different, and the formula you get here is not going to hold.